for the recording's purposes, I suddenly have a cognitive dissonance here when I see that it says to treat it as inelastic. Inelastic, quite technically, simply means that you didn't conserve kinetic energy. But I said in practice, we're going to treat inelastic as they stick together and travel at the same speed. And we're being asked to find kinetic energy when it leaves if it's traveling at the same speed. So I'm going to go ahead and do it with that assumption, and then we'll see how that plays out. So we start with our kinetic energy initial is 1/2. What's the only thing moving initially? The bullet. So 1/2 the mass of the pellet times the V pellet squared. And our kinetic energy final, now this is going to be final like immediately after the bullet goes through, not the kinetic energy after it started swinging. So it's just started moving, it's still all horizontal. And so it'd be 1/2 mass of the pellet V final squared plus 1/2 mass of the block V final squared. I put V final squared for both because if it is following the rules we have for an inelastic collision, those should be the same final speed. So this is my condition for inelastic. And so if I take these all into play, oh, I see that looking at their answers, they're taking the height it goes to into play as well. So they're saying that this here, the kinetic energy that the bullet has is going to all be conserved into the height it swings to. And so we're going to have, for the last part, oh, yeah, that's right. That it's going to swing up, so all of that kinetic energy is transferred into potential energy. And this here is the kinetic energy of the pellet after the collision that we're looking for. So what they called KP, right? Everybody agree with that? So if I want to solve this for kinetic energy of the pellet, I'm going to have so using this substitution here, I put my kinetic energy is equal to initial is kinetic energy final, which I substituted the kinetic energy of the pellet plus the mass of the block GH. And so if I solve that for kinetic energy of the pellet, and it has it, it does not have anything so simple. So that means I must be misunderstanding the question, right?
Why is kinetic energy initial equal to kinetic energy final?
Yeah.
You're right. It's not.
Yeah.
Maybe Richard Webb. Okay. That I didn't want to do. Crap. Well, now that's half done. Let's do it all. You're right. It's, wow. That's a very good question and one that I messed up. I like it better when I don't make mistakes. So it's not kinetic energy conserved because it's not elastic. But we do have momentum. Momentum initial is equal to momentum final. So that means mass of the pellet times V of the pellet is equal to mass of the pellet V of the pellet prime, or I'll just call it V final, plus mass of the block V final. Okay, that's my actual correct equation. And so this allows me to find then that V final times mass of the pellet plus the mass of the block is equal to mass of the pellet V of the pellet. But they didn't give me V of the pellet. They gave me the kinetic energy. So I have to now use the kinetic energy equation to determine what the V of the pellet was. What did they call it? They called it K0. So that's what I'm going to have to use for V of the pellet. Now you notice I can cancel the MP somewhat and have just an MP on top. That is combining this here, put it in a square root and make it squared, and then combine those together. And it's the same as putting an MP on top there. So I got to make another page. I'm glad you guys actually corrected me on my little mistake, because that, well, sorry, hit the wrong thing. Page manipulation. Excellent. I broke the software. It's stuck. Okay, good. Still won't allow me to put another page in. Okay, well, we won't put another page in. We will find another way to do this. So that's the V final we found. And so the kinetic energy of the projectile in the end is going to be found by just taking one half mass of the projectile times V final squared. Oh, but we have to relate it to the height. That seems like it's really good so far, doesn't it? Does to me. I really need another page. I need to back off of my inelastic collision. It's now clear, right? My inelastic collision, having them have the same final speed, gives me an answer that just does not have to do with how high it swings. So I'm going to have to back up and solve it as if they didn't say that inelastic. And so I'm just going to work here. So I'm actually going to go back to kinetic energy initial, using their terminology, 1/2 m pellet V pellet squared. Therefore, V pellet is equal to square root of 2 K0 divided by MP. So that was our first thing. My conservation momentum, P initial, equals mass, and now the pin stopped. There's no reason for the pin to stop here. It's got to be a software issue, right? It's got to be. Since already we've seen this program having failure. going to try stopping the program and
Well, it's still showing up. It's just not drawing anything.
yeah, which is why I think it's got to be a software issue. It can't be a digitizer issue because if it was the digitizer, it wouldn't pick it up. I didn't save it.
I think you were on slide.
Oh, was I? Okay, good. Whew. Please work. I used V pellet final this time. And so my momentum final is going to be the combination of the two. And now I will use my energy conversion in the block as it swings up. So I have the block here with V block final, and it swings up to height H with V final equals 0. And so in this transition, I'm going to have kinetic energy initial equals 1/2 mb VB final squared. Potential energy initial is equal to 0 because I'm going to set my reference there. And kinetic energy final is 0. Potential energy final is mass of the block GH. And so for conservation of energy, this is what I did in my head on the first one because this is a little more complicated. I write it out. So I'm going to have 0 equals final minus initial kinetic energy plus final minus initial potential energy. Therefore, VB final squared is equal to 2GH. So VB final is square root of 2GH. So now I can put that VB final in for my momentum final and find on the left side, when I multiply both sides by MP, that's where I'm going to put it inside, and I'll have so this is my equation now that will give me the speed of the projectile final. And now for the last part, kinetic energy. I don't have space to put that there. What kind of crazy man am I? So I have to square that thing that I have above. this MP squared on bottom is from the squaring of the velocity, and the 2 is from the 1/2. So that should be a correct answer, that I didn't have to take their statement of inelastic to mean anything special at all. So I just ignored the inelastic words, and I have an equation that, if you look at theirs, they were smart and said we can cancel one of these MPs. So it should have 2 MP on the bottom, which rules out only 1. And on the top, we should have the square root of 2K MP minus MB2GH. So on mine, it's this one, which of course you can't even see what I'm clicking. And it says continue. So that is the correct interpretation. And then part B, solve numerically. Once you have it here, you can solve numerically.
Thank you.
Yes, that took longer than anticipated. But I feel better having done it.
Can you go back to the
To here?
Yeah.
Remember, these do get posted up after class, so you can look at the slides. You can go watch it on YouTube and say, see? It wasn't easy for him either. It took him time. He made the wrong assumption. He misinterpreted the problem. But don't do that. Don't mock your teacher. We have fragile egos. Okay, so what I'm going to talk about today, first thing I'm going to do is to answer a question that people always wonder about and probably get the wrong idea. What would happen if we were in the really crummy remake of, and now I forget the movie. How's that work? It's not my trip. Total Recall. You guys have seen the really crummy remake, right? No? Okay, well, in the really crummy remake, they have an elevator that takes them from one side of the earth through the center of the earth to the other side of the earth. Have you guys seen that? Nobody remembers? Okay, thank you for remembering, Megan. So in the video, in the movie, they show everybody sitting here in this car, and everything's normal, blah, blah, blah. And then when they get to the center, all of a sudden, they're weightless, and boom, they slam over to the other side, and then they go up to the other side of the earth. So basically, it was like they had normal G until you get to the center, and then you're weightless for a split second as you go to the center, and then your normal weight going up. That's what they portrayed in the movie. Because, of course, they didn't ask any scientists at all what would happen. So let's look at what you would have. Now, keep in mind, this elevator is moving really rapidly because they get to the other side in something like 30 seconds. So they probably had a really big acceleration going down. Yeah, I know. So a really big acceleration going down. They probably should have been pushed up against the ceiling as it was accelerating downward. And then a really big acceleration slowing them down when they're going back up and pressing the ceiling on both sides. But once again, they didn't really pay attention to how it would work. They didn't have any crazy stuff like that. They just had an airplane that takes you to Mars, and that was all that was going on in Total Recall, the original. So we're going to do that first. Then we're going to talk about center of gravity. Should time last that long, which it won't because we spent our time doing the homework problem. So here is a fairly realistic graph of the density of the Earth as you go from the crust through the crust, through the mantle, through the liquid core, and through the solid core. Now, I looked at some other resources, and there is actually a discontinuous jump right here, but this graph doesn't show it, and we're going to make some approximations to make our lives easier that is even worse than that, shall we say. By the way, can you all agree? I think we've settled that it was a software issue.
Yeah.
Okay. Just want to make sure we're all on the same page on that. Software issue. So what do I do when this happens in class? Kill the program and restart it, right? Okay. You're all my witnesses. So first, let's make a dumb approximation to solve this problem. Then we'll make a better approximation, and we won't make the best approximation because I couldn't find somebody who's already done regression to find fits to those. So first, the dumb approximation. Let's assume that the Earth has a constant density equal to its average density. What would happen to the acceleration of gravity as you went down through the Earth if that was true? Well, the way you calculate that is we know the force of gravity, what we learned in class, gm1m2 over r squared. Well, if we're going to work with a continuous mass distribution, then we're actually going to have df, I have the equation right here, df is equal to g m1 times dm. What is m1? M1 is the object that the Earth would be interacting with. For instance, if you were going down through the Earth, M1 would be your mass. And then dm is a little tiny piece of mass at some position, x, y, z in the Earth, and you have to add up all of those little pieces of mass. Well, in calculus, how do we add up all those little pieces of mass? Integral, right. So we're going to have to integrate this up. Now, to make life a little easier, since the acceleration of gravity, g, is defined as the force of gravity divided by the mass of the object we're looking at, then I can just divide out the m1. And so dg, the acceleration of gravity g, is capital G dm over r squared. Now, we just said what dm is. Dm is a little piece of mass. Well, that little piece of mass is associated with a little piece of volume because we have a real object. So we're going to have change tool. We're going to have dv, and depending on our coordinate system, dv could be dx, dy, dz. That would be if we were using Cartesian coordinates after Rene Descartes. Or we could have dv equals r squared sine theta dr d theta d phi if we're using spherical coordinates. Or we can go to something that's intermediary between those two. How many people have done an integral using dv equals r squared sine theta dr d theta d phi? Okay, three, 4 people. I will show you how to do it this way, and I will also show you how to make it easier. This way is actually very easy, but to make it easier in that you don't have to think about a triple integral. So our dv, I'm going to use spherical coordinates for the very obvious reason that I have a spherical symmetry in the Earth. You choose your coordinates to match your symmetry. That's why we have spherical coordinates, because they make problems easier if you have a spherical symmetry. If you have a cylindrical symmetry, then use cylindrical coordinates to make it easier. So we're going to need to use spherical coordinates no matter what we're doing. And so I'm going to use spherical coordinates, and we're going to work from there. Now, I have dm. The mass has to relate to the volume by the simple definition of density. Density is defined as the mass over volume, which means that dm must be equal to the density dv. So this is the relation that I put in to my integral. So I have dg is capital G dm over r squared. I'm going to now write dg is equal to capital G times rho dv over r squared, making that substitution. Going further with this, our first approximation was saying that the density is the average density of the Earth. And then for dv, I'll put in r squared sine theta dr d theta d phi. And of course, it's all over r squared. And that's really, really convenient, because what happens with my r squareds? They cancel out. Woohoo! Life is, a little bit better here. And so I end up with the dg that I have to integrate is is that. So, is my work going to be hard? I'm going to go with no. If you look at this, R shows up only one place in dr. Theta shows up two places in sine theta and d theta, and phi shows up only one place d phi. So when I integrate this, I'm going to have the integral of dg is equal to, put my constants outside, g rho average. I have a triple integral of sine theta dr d theta d phi. And it's that triple integral that people here haven't seen by and large. So how to treat the triple integral can be easy or hard. In this case, it's easy. Hence, I don't feel bad about doing it. It's hard if your limits depend on variables. But in this case, our limits don't depend on variables. What's the limit for radius? What's the smallest radius you can have for a sphere? 0. And what's the maximum radius for the Earth? Our Earth, right? Those limits were easy. Now we have the other two, theta and phi. What are these angles? One's the altitude angle, one's the azimuthal angle. One is telling us basically, well, you can do it two ways. You can do the angle from the North Pole downward, or you can do the angle north and south of the equator. For our sine theta, it needs to be from the North Pole. And so theta is going from 0 at the North Pole to what would the angle be at the South Pole? Okay, we like to use radians for the most part, so to pi radians. And then phi. Phi is the azimuth that's going around the Earth. Well, what's the angle? What's the small, you start at 0, what's your maximum angle if you go around the Earth? 2 pi. So the phi goes from 0 to 2 pi. Now I'm going to put above this what each one was, just so we keep those tied together. That's one of the things that can confuse you. Question, Brady.
Wait, since dr is listed first, isn't the boundaries for R the last integral?
You will find different textbooks and different people that put the orders differently. So that's why I put those above, so we know which one's which. Here's the way I like to do it. If my integral is separable, if I can separate my functions of r and theta and phi, then my life becomes real easy. And I rewrite this as integral from 0 to radius of the Earth dr, integral from 0 to pi of sine theta d theta, integral from 0 to 2 pi of d phi. That way there's no confusion because I have the d with the integral. Some people actually put the d's with the integrals and then they put the integrand following. Right? There's lots of different ways to write a triple integral. It's important to realize which integral sign with limits goes with which variable. But the way this works out, we can do each one of these integrals independently. What's the integral from 0 to 2 pi of d phi? Or d phi if you want to call it phi. That's just 2 pi. What's the integral from 0 to radius of the Earth of dr? And what about the integral from 0 to pi of sine theta?
Negative cosine pi.
You've got to put in both limits. So the integral of sine is negative cosine. So I'm going to have negative cosine of pi minus negative cosine of 0. If you forget the lower limit, you're going to get the wrong value. Well, what is cosine of pi? Minus 1. And what is cosine of 0? 1. So I have minus a minus 1, minus a minus, or minus a 1, which turns out to be 1 plus 1. Right? In physics, we can make the easiest math problems sound hard. 1 plus 1 turns out to be, yeah. So we have radius of the Earth times 4 pi is what we got from that. So that's the G at the surface of the Earth, but I said I wanted to find the G somewhere inside the Earth. Well, if I want somewhere inside the Earth, what would I have done differently?
Change your radius.
Change the limit for radius. That's all I have to change. Now, keep in mind, we already saw from Newton's synthesis that the mass outside of your radius doesn't matter if it's spherically symmetric. It's only the mass closer to the center than you are. So it's perfectly correct to say G at any elevation is this function, just replacing capital radius of the Earth with the radius I'm at. And what's the easiest way to write this? Well, since this is G, I'm just going to substitute. The acceleration of gravity is a function of depth, or excuse me, radius from the center, is just the acceleration of gravity at the surface times the ratio of how far you are from the center. Now that's real simple, and that's easy to say. Okay, so the acceleration of gravity just linearly decreases until it gets to 0 at the center, and then it linearly increases as you go to the other side. But this is naive. What's naive about it? Yeah, the density is really changing. If we go back and look at our picture, in our picture here, we see that the average density is pretty much the density that you have at the boundary between the molten core and the mantle. And so you have a higher density in the intersection. So the inner, a little over 3,000 kilometers, it's the inner 3,486 kilometers, has a much higher density than the outer, roughly 3,000, just under 3,000 kilometers. And so that's going to make our answer fairly different. Now, if you look at the other part of this figure, you see that the acceleration of gravity is highest here at that boundary. So the acceleration of gravity in reality actually increases as you go down until you get to the molten core, and then it starts decreasing. Can you explain that by hand waving before we do any math? Why would it be going up as you're going down?
Because your distance to it is decreasing, and that
Okay.
increases.
Your distance to the more dense material is decreasing. Even though you have less dense material that you're leaving behind, it's no longer affecting you. You're getting closer to the more dense material, and so it's becoming a stronger effect. So let's try to model this a little better. Now, we're not going to get the same answer as the correct answer because we're modeling it incorrectly knowing that. But what I'm going to do is simply model this as if it's a straight line. That was the wrong tool. A straight line relationship, that it's linear. So I'm going to say that for that first portion, the density inner is equal to the density that it has at the center, which if you look at this, that's just a little over 13. So I'm going to say, 13 and a half grams per centimeter cubed. And then minus, because it's decreasing, and I just have to find the slope of that line. So it's going to be a difference of going down to about 9.9 from 13, let's say 13.5 to 9.9. That's a change of 3.6. Divided by the distance, which is 3,486 kilometers, and then times the radius. So that is an equation for the density in the center portion. We know it's not correct. It's actually going a little closer to the line than what I drew because I went to a little higher. The 13.5 is a little higher than where the line ends. So we'll use that for the density in the inner portion. And then for the outer portion, we'll once again linearize it. I swear, today is an all-time good day. Linearize it so that we will say the density in this region is approximately equal to, and I'm going to do the same method, starts at 5.5 grams per centimeter cubed minus 5.5 to, what'd you say, 3.5-ish? Okay, 2.2. I'm good with that. Actually, 2.2 is the correct number. I don't know. I doubt you looked it up. So 5.5 to 2.2 is 3.3. Divided by that distance from there to there, which I actually didn't do those numbers, but it's 228. Is that 85? Yeah. And then I have to multiply this one by R minus 3486 because I didn't start at 0. So we have two different equations for the density for the two different regions. Now for my method, I go through and do the same thing. I'm running really low on time, so I'm not going to have time to actually complete the calculation, which is fine and dandy because I'd have to do a lot of unit conversions before I could start if we wanted to actually get right numbers. But I would have two different regions, so now I would have to do the G real is equal to capital G times the integral, triple integral. The first one goes from 0 to 3,486 kilometers of density inner I got to put, and I'm just putting density inner dV over R squared just so I can save myself writing, plus G times the integral from 3,486 to radius of the earth, the other two, rho outer dV over R squared. So I have those two integrals. And I should, if I do this entire integration, do both integrals, which is going to be a little more complicated now because I now have my density as a function of R, not as a function of theta and phi. So those parts are still going to give me the 4 pi. But I'm going to have the integral of the density function I had that has R in my dr. So it's a little more complicated. And if I am further out than 3,486, then I do this one to the top one to its completion, the bottom one out to whatever radius I am. If I'm closer than the 3,486, then it's only the inner one that I do and I do out to its radius. So that's how we could find a better measurement and come closer to getting the actual numbers for the acceleration of gravity as you go through the Earth. And so, of course, just taking these, what you'd find is acceleration of gravity slowly goes up as you drop through the mantle and then goes down rather precipitously from there on. That's interesting, right? And that's a use of our calculus in physics. Oh, so here's what the new material was. Moments of inertia. We haven't talked about in class yet, so it's okay that we don't know that. The center of mass, though, we have. Center of mass, in general physics, we had that equation. The sum of each piece of mass multiplied by its position divided by the sum of all the pieces of mass, a weighted average. How do we find the center of mass if it's a continuous distribution instead of like 3 balls? Continuous means I have to integrate over all the little infinitesimal pieces. So as I do this, you have to decide which pieces are the little pieces. Is it the xi's that are the little pieces or the mi's that are the little pieces? M is correct. Because the x is the distance from the origin to wherever you are, that definitely is going to become large. But the m is how much mass is at each location. That's the thing that's small. So for calculus, this becomes, replace the summation sign with a bigger S. So there's the calculus variation of that same equation. That wasn't very hard, right? Now, the math, of course, gets harder, but just seeing the translation between the algebra base and the calculus base, that's pretty easy. And of course, this lower one, we haven't learned it yet, but once again, it's going to be DMs, but the R is an R perpendicular, so we'll not worry about this for now. We'll worry about it later. So here's the equation that we would use. Now, because I only have 0 minutes left, I'm not going to do my first example, which is really simple. Instead, I'm going to go back to the calculation on the sphere and say, how could we have done that easier if people didn't want to use a triple integral? Right here. Oftentimes, you can find a function, if you have something that is spherically symmetric, using my spherical coordinates, if it's spherically symmetric, I can find a function for the area on a spherical shell. That function is very simple. Area of a sphere is 4 pi radius squared. And so I could replace the sine theta, d theta, d phi integral with, well, and the r squared part, with 4 pi r squared. That is, I would just have the integral of 4 pi r squared dr, which is in essence what we had because we integrated out real quickly what the phi and theta parts gave us. So you can just use that 4 pi r squared times dr as dv. If you have a uniform spherical distribution. If it's not uniform spherical, well then you can't, right? If your distribution has to do with theta or phi, then you can't simplify it that way. So when you looked back at that work, actually, yeah, it was on this page. When you looked back at that work, we had the simple 2 times 2 pi. Those integrals were easy to do. But if it made you uncomfortable having to do that, you could have just said right from the get-go up here that, where was it? dv is equal to area of a sphere dr equals 4 pi r squared dr. And it would have given you the same outcome. You just would have had a single integral over r. Only possible if there's no theta or phi in your function you're integrating. Okay, we're out of time, so that's where we stop.